Welcome dear friends, once again for session based on buoyancy and flotation. Today we are going to solve some university asked problems. Let us begin with the problem number 1. So friends, let us begin with the first problem. A cone of specific gravity capital G is floating in water with apex downwards. It has base diameter small d and vertical height small h. Show that for stable equilibrium of the cone, h is less than half of in the bracket d square into g raised to 1/3 upon 1 minus g raised to 1/3 and whole raised to half. This problem has been asked in previous university examination. So let us begin with first its solution. So let us begin with the problem. This is cone. This cone, apex downwards, floating in water. Apex downwards, floating in water. Apex downward and floating in water. Let us say this is small d, and at the water surface this diameter becomes d1. This diameter is d1. Let us this height of water surface be h1 and the total height of the cone is h. Okay. Now let us G is center of gravity of the cone. Center of gravity of cone. B is center of buoyancy. H1 is height of cone immersed. Height of cone immersed. D1 is diameter at water surface. At water surface. D is diameter of the cone. And W is unit weight of water. W is unit weight of water. Okay. D1 is the diameter at the. So weight of water displaced. Weight of water displaced is equal to weight of cone. So pi d1 square. So pi d1 square h1 into w is equal to pi d square h into G into W, into G into W. Okay. So from which d1 square, pi and pi get cancelled here, pi and pi get cancelled here. So d1 square h1. So d1 square h1 is equal to d square h into G into G. So let us say this is equation number 1. Equation number 1. Then again d1 by d is equal to h1 upon h1 upon h. That is equal to d1 is equal to d into h1 upon h. Equation number 2. Equation number 2. Substituting 2 in 1. Substituting 2 in 1. Substituting 2 in 1. Substituting 2 in 1. h1 is equal to h into g raised to 1/3 into g raised to 1/3. You remember this formula throughout, because for solving such cone problem this formula is very important. In some books you will find this expression as, instead of L1 it is L H capital H s raised to 1/3. Remember this formula always. This formula is universal formula for solving immersion of cone problems. So this is equation number 3 now. This becomes equation number 3. This becomes equation number 3. Then now BG is equal to, what is BG here? So let us draw this vertical axis here, and this is G here. This point is G. This point is G here, and this is B. This point is B here. So BG is equal to 3 by 4 H minus H1. H minus H1. So 3 by 4 into H minus H G raised to 1/3. G raised to 1/3. From equation number 3. From equation 3. If M is metacenter, now if M is metacenter, then Bm is equal to I upon V. That is equal to pi d1 to the power 4 upon 64 divided by 1/3 pi d1 square upon 4 into h1. That is equal to 3d1 square upon 16h1. 16h1. Let us say this is equation number 5. Let us say this is equation number 5. Now substituting equation number 4. Equation number 4. This is equation number 4. This is equation number 4. Substituting this equation number 4 and substituting tuting 2 and 3 in 5. 2 and 3 in 5. So 3d1 square, sorry, so BM is equal to 3 by 16 d square g raised to 1/3 upon h. So this is equation number 6. Now for stable equilibrium, what is our condition? BM must be greater than BG. Therefore 3 by 16 d square g raised to 1/3 upon h must be less than 3 by 4 h minus h g raised to 1/3. Simplifying h must be less than half of d square g raised to 1/3 upon 1 minus g raised to 1/3 raised to half. So this is proved. So in books you may find like this way: L square less than 1 by 4 diameter of the cone d square, specific gravity of cone material s raised to 1/3 upon 1 minus s raised to 1/3. This way also can ask in the examination. So I will rewrite the equation here once again. So our equation is h is less than half d square g raised to 1/3 upon 1 minus g raised to 1/3 raised to half. Or in other words, you can write like this way: L square, because this is h is replaced by here h, because h is the total height of the cone. So this is H. In some book it is also written as L. L also here. Okay. So this is L square is less than 1 by 4. Just we are squaring the things, nothing else. D square, capital D is this D. D or D. D square, cone material specific gravity 1/3 upon 1 minus S raised to 1/3. So this is solution to the problem. This is proved. This is proved. Okay. Now let us discuss with another problem. So let us begin with problem number 2. A cone floats in water with vertex downwards. If the specific gravity of the cone material is 0.7, find the least apex angle of cone for stable equilibrium. So in this case, so first of all we'll draw the diagram. Immerse portion is small h. Immerse portion is small h. Immerse portion is small h and height of the cone is capital H. Is capital H. Okay. So let S is specific gravity of cone material H is depth of immersion. Depth of immersion. So weight of the cone is equal to 1 by 3 pi r h sw s into w, which is equal to one third this is alpha or theta. This is theta. This angle is theta. So one third h tan alpha, tan theta. In some book it is also written as tan alpha. So therefore I am using alpha. So tan theta square into h into sw, which is equal to one third pi h cube tan square theta sw. Okay, so now find out weight of water displaced. Weight of water displaced. So which is equal to one third pi r square. What is r? Radius at immersed portion. Radius at this radius, and this is capital R. So pi r square h into w is equal to is equal to one third pi h, now small h tan theta whole square into h into w, which is equal to one third pi h cube into tan square theta into w. Now equating these two, equating equation number 1 and equation number 2. Equate this equation number 1 and 2. So one third pi h cube tan square theta into w is equal to one third pi h cube tan square theta into s into w. So pi get cancelled here, w get cancelled here, tan square theta also get cancelled here. So what will remain here? One third also get cancelled here. So what will remain? H cube is equal to h cube into s. Similar to this equation, small l is equal to l s raised to one third. Remember this equation for solution to the floating cone problem. Immersed portion L and full length of the cone and specific gravity of cone material. You know this formula, you can use directly to solve such type of problem. Okay, don't derive much, spend the time on derivation. So H is equal to H S raised to one third. Now the problem is very simple. Now for stable equilibrium, for stable equilibrium, 2 theta is apex angle. 2 theta is apex angle. So sec square theta is equal to h, capital H upon small h, which is equal to h upon h s raised to one third. So cos square theta is equal to s raised to one third. Now the problem is very simple here. So cos theta is equal to s raised to 1 by 6. S raised to 1 by 6. So cos theta is equal to s raised to 1 by 6. Already we have obtained here this. So cos theta is equal to, what is the specific gravity of cone material? It's 0.7. So 0.7 raised to 1 by 6. 0.7 raised to 1 by 6. So cos theta is equal to 0.9422. So theta is equal to 19 degree 33 minutes and 38 seconds. So 2 theta is apex angle. Which is equal to 39 degree 7 minutes and 17.9 second. So this is the solution to the problem. So this carries 7 marks asked once upon time in university examination. Okay, this completes the second problem in today's session. Yes. So let us take another problem, number 3. A solid cylinder made with a material of specific gravity 0.8 is 30 centimeter in diameter. What is the maximum permissible length of the cylinder so that it can float in water with its axis vertical? This is the problem asked in the university examination. So let us begin with this diagram. So this is diameter D here. L is the length of the cylinder. O is the apex, the bottommost apex point. B is the center of buoyancy here. G is the center of gravity, and M is the metacenter. And Y is the immersion, which is equal to SL. Which is equal to SL. Okay. So important step here: weight of the cylinder is equal to weight of the water displaced here. Okay. So pi d square upon 4 into L into W into S is equal to pi d square upon 4 into Y into W. So Y is equal to SL. Y is equal to SL. B is center of buoyancy. B is center of buoyancy. So OB is equal to Y upon 2, which is equal to SL upon 2. S, what is S? S is the specific gravity of that wooden cylinder or floating cylinder. Okay, and BM as usual I upon V, which is equal to pi d to the power 4 upon 64 whole divided by pi d square upon 4 into SL that is equal to d square upon SL, that is equal to d square upon SL, Okay, and OM is equal to OB plus BM. OB is SL upon 2 plus BM. BM is what? D square upon 16 SL. D square upon 16 SL. D square upon 16. So for stable equilibrium, for stable equilibrium, OM must be greater than OG. This is OM. OM must be greater than OG. That is SL upon 2 plus D square upon 16 SL must be greater than or equal to L by 2. Must be greater than L by 2 because OM is L by 2. So L by 2 minus SL upon 2 must be less than or equal to D square upon 16 SL. So L by 2 minus SL upon 2 must be less than d square upon 16 SL upon 16 SL. So L by 2 into 1 minus S is less than d square upon SL. D square upon SL. So L square, L square must be less than d square upon 8s 8s into 1 minus s into 1 minus s. Okay, so L must be less than d upon 8s, under root 8s into 1 minus s into 1 minus s. Now in problem what he has asked, if d is equal to 30 centimeter, if d is 30 centimeter and s is equal to 0.8, substitute the values accordingly in this formula. So L must be less than, we'll get L must be less than 26.51 centimeter. This is the answer for problem number 3 asked in the university examination. Now this completes the chapter buoyancy and flotation, chapter number 4, and accordingly we have also completed the entire fluid statics. The fluid statics, which was composed of 4 chapters, that is fluid properties, measurement of pressure, hydrostatic pressure, and buoyancy and flotation. So these 4 chapters we have already completed in fluid mechanics 1, and if you want some problems we will take it later on. But now let us begin with the second part of the subject fluid mechanics 1, that is fluid kinematics. So fluid kinematics is free motion of fluid particles or free motion of fluid flow, that we will cover in the next session. Okay, those who have not subscribed my channel, or those who are new to this channel, and those who are watching this channel as an audience, I appeal and request them to subscribe this channel, Civil Engineering and Law subjects. Thank you.